Hello. So today I would like to present VISIR. VISIR is an infrared camera and spectrograph at the VLT, and we will go quickly over the status of the instrument and some improvements recently, and of course the latest results. Now, I'm presenting a work that has been done by many people at the VISIR IoT. That includes, for example, the instrument scientist Konrad Tristram, includes the USD support scientist Mario van den Anker, and many others, too many to count. What is VISIR? There is a lot of stuff here on this slide, and you can read it all in the excellently written VISIR user manual. I'm not going to bother you with pixel scales and resolutions. It's all there. The document is one of the finest user manuals that I have ever seen. Okay, I highly recommend to read it before going to sleep. Now, what are the new things about VISIR? Recently, VISIR acquired an L-band filter at about 3.7 microns. This filter is not offered yet, but it will be hopefully very soon. And this was meant to fill in the gap that has been opened after the decommissioning of NACO and Isaac. Of course, we will have full pipeline support for the new filter, including image alignment combination and flux calibration. On the plot here, you can see that various filters. This, as you can see, is the bluest VISIR filter. When you see this slide, you probably should realize that I slightly misled you with the title of my talk. It's really about the pipeline improvements. Recently, we have revamped the pipeline, and it has acquired a number of new features. I'm sure you will like them. For those of you who are familiar with the ISO reflex lengua, the orange square around the spectral extraction actor should speak clearly one word: interactivity. And this means that now you have much more flexibility about how to extract spectra. And this is a snapshot of the new window that you will see when you reach the extraction actor. Before, we only used to have optimal extraction, which is wonderful. But optimal extraction works only if the profile of your object, the spatial profile, does not change or changes very slowly with wavelength. So if you have an emission line that is not following the profile, the stellar profile, because of disk, or if you observe a galaxy that has emission lines, different emission lines in the disk, then you're in trouble. And so now what we offer is a way to rectify this and do it as a part of the pipeline, not within using other external tools. You can define many apertures, and you can see here they're organized in layers. This is one layer, this is another layer with a different set of apertures. You can define different widths, you can move them around to have different centers, and you can have different extraction algorithms applied. One, of course, is the optimal extraction, and another is extraction by summing within a fixed width aperture. Even in that case, in the later case, you have different ways to treat the sky. You can take an average or median, or just fit a line across along the spatial direction across the continuum and subtract that way the sky. You can have multiple apertures within a layer as well. And that allows, and you can see that on the left, that allows you to extract simultaneously apertures from different orders. Which means that unlike before, you don't have to run the pipeline separately for each separate order. You can do it all in one go. On the right, you see multiple apertures within a particular order. And I used aperture extraction here just to show you the effect on the final extracted spectra. Of course, the wider apertures have more signal. The narrower apertures have less signal, and this is all aperture extraction, okay? The wider apertures encompass the entire spectrum. The narrow apertures lose a lot of light, and therefore the signal to noise goes down. Just for the sake of demonstration, I also did optimal extraction versus aperture extraction with external tool. The orange line is a spectrum extracted with IRAF, and then you can see the difference is enormous in terms of signal to noise. The scatter is much smaller with optimal extraction. The next thing we plan to do is to have MolecFit integrated in the pipeline, which should make the processing even easier and seamless, because you just click a button and it's all done. You only have to write the numbers in the paper. But be patient, this will come. Now a few words about the science. As of a couple of days ago, there have been about 250 publications with VISIR, okay? That may not be as much as you see from Muse or from X-Shooter or from Force, but we should remember that this is a relatively narrow niche instrument, and there are only on average about 15 proposals approved per semester, 30 per year. So that's not that many. On the left, you see how the number of papers per year has evolved according to our internal ISO telescope bibliography service. On the right, you see a similar plot, but based on ADS, and there is no easy way to identify all papers. I only looked for papers with VISIR and VLT in the abstract, so it identified about half of all the VISIR papers. But you see almost very similar structure, and this gap here is because for a while VISIR was out of service for replacement of the detector. But so we are going up now, and I keep hoping that after this meeting we will see even more papers coming out. As I said, this is a niche instrument. We should remember that and be careful when we compare it with other instruments. Just a few words about the demographics of the papers. About half of them are published in ANA, and this is not surprise because for most European astronomers this comes without paid charges. About 1 out of 4 papers uses either completely or partially archival data. And out of these 249 papers, about 40, which comes to about 1 in 5, also use NACO. And the other instruments that have some noticeable synergy with VISIR are MIDI, ISAC, and SOFI. But I guess this is going to change soon, and X-Shooter will come up because these are papers that have been written in the last 15, 20 years, and now these instruments, ISAC, MIDI, and NACO, have been decommissioned. The archival usage is still not as high as we would have liked, and I encourage you to go into the archive immediately after you listen to this talk and to see if there are any VISIR observations of your favorite objects, okay? This is a snapshot of the highest impact based on number of citations, papers from VISIR. And I'm not going to ask you to read all this. Just look at the colors of the highlighted words. Red are AGN papers, okay? 3 out of 10. Disk papers are green, 3 out of 10. X-ray sources, 2 out of 10. 1, 2 out of 10 stellar papers. Now, let's look at, for the same, at the 10 latest papers, and then what we see is a very different demography. 2 exoplanet papers, 1 Uranus solar system planet paper. The exoplanets come from near, of course. 1 disk paper, 1 black hole candidate paper, 1, 2, 3, 4 stellar papers, okay, and 1 instrumental paper. So the demography, the kind of science that VISIR has been doing has changed quite a lot. I left aside this very important paper. Well, first of all, it was not among the 10 latest papers, and second, it deserves a few words on its own. This is the discovery of a low-mass planet within the habitable zone of Alpha Cen. And I'm sure this is going to soon, this is going to climb to the most impactful VISIR papers. Before finishing, I would like to underline that everybody, astronomers from everywhere, can apply for observing time with VISIR. You don't have to be from a ISO member country. I strongly encourage you for the next call of the proposals to see if you can do any science, if you can do your science with VISIR, okay? And at the end, of course, I would like to remind you that this is the greatest medium-infrared instrument, especially in the southern hemisphere, because it doesn't have any competition. Okay? Thank you. Bye-bye.